just wait a few seconds. People connect. Start. Thank you again for joining us for this last session of the user conferences. After we'll have a final words from our marketing manager. But for the last session, I'm pleased to introduce you again to Amit Kumar from PSIM team. So PSIM, as a reminder, is the developer of PSIM software, and Amit is a technical application engineer with PSIM. He completed bachelor degree from NIT Ahmedabad in India and master degree from Queen's University in Canada, and is a prime developer of design tools related to Resonant LLC, CLLLC, and some other power converter style inside PSIM. Super suite, so on. He also part of the technical support team, the strong technical support, and is part of this team. Thank you, Amit, for joining us again today. So we will dive directly into your interesting topic.
So can I share my screen and start, Matt?
Yes, you can.
Okay. Okay, so just let me know when I change from slides to simulation, whether you can see it or not.
Mm-hmm. Okay, no problem.
Okay, so I will just start it now. Yeah, so hi everyone, welcome. My name is Amit. I'm an application engineer with PSIM, and we are the maker of the software PSIM. So today we are going to see how we can use tools related to resonant converters in PSIM, and how they are going to help you in quick, fast design in automated fashion. So we will be looking at our tool chain, design tool chain for resonant converters in PSIM. So I will be just going through a few of the slides, and then I will be showing mostly live action of our design tools, and you can see how it's working, and later you can ask any questions if you have. Yeah, so we are now offering these design tools. I will also go in detail when I will do live. So first is steady state solver. So as the name suggests, we solve very instantaneously steady state. So that is going to help you in very fast waveform analysis. You can check boundary conditions, soft switching. You can see all the output parameters like peak, RMS, DC gain, and all those things using the solver. Design curve tool we also have to compare your gain curve or RMS curve or any other curve at different quality factor, magnetic ratio, or any other design curves. We have a list of a set of design curves, which I'm going to show you too. Excel design file is generated something based on, as we know that for resonant converters, we operate in certain frequency range. So Excel design file is generated in that frequency range. Based on your selected Q and K, we find the frequency range for your gain requirement for, let's say, that particular application. And this Excel file is going to help you. You can basically sweep there different values of Q, K, essentially LC and LM, your magnetizing inductance to select. So we have added a new, so all these are in our current version of PC. We have added a new template for Resonant CLLLC. So all right now we have for LLC and a fourth order. Now we have added a fifth order template too, and we are going to see that also in live action. So a little bit of background, just I want to go quickly. You can have this slide and read about. So you can see that our tools is based on time domain. By time domain means that we actually analyze the circuit. We don't do any approximation. We do not. We consider the actual switching model of a circuit, whether it's a diode or switches. And based on that, we have analyzed the circuit in different modes. As you may be knowing, that resonant converters have lots of mode, and resonant converters have different modes as you change your frequency or load or any other factor. So based on that, we have analyzed it. We have a numerical closed form answer in some cases, and some cases we have a direct closed form answer. From that, we have made all these tools I was talking about here. And so this is something I wanted to show in the right, is that this is what typically people do in most of the application note or papers you see. is based on, so this is good to do. It's a fundamental harmonic, as the name suggests, this is a approximate model, and this gives you easy to use fundamental equation based on your own, because you are only considering fundamental sine wave here. If you do time domain, you need to consider all the harmonics on input side as well as output side. So this is something we are not doing. We are doing time domain. So that's why everything is accurate and precise as compared to the simulation or any thing. So you can ask questions, and you can later too if you have any doubt here. This is how our template is going to look for Resonant LLC. So we have its Resonant LLC template from our last release, and these tools will be there. I will be showing you. And this is for our new template for Resonant CLLLC. So this is a fifth order template, a generic fifth order temp. So this is also gaining a lot of attention these days. This particular tank in bidirectional operation, mainly in medium power range. And because of the DC blocking capacity, you can see it have from the both side. Also, you have more degree of freedom to design actually your gain carry function of to capacitance ratio or to inductance ratio, and you can have a more degree of freedom in designing parameters. And also you can utilize the parasitics of the transformer more efficiently using a more higher order tank, as you say, like, so you can take into account a perfect T-shaped transformer to have this kind of a tank. So what I will do, I will go back, go to in simulation and show you our tools in live action. So this is the welcome page of PSIM, right? So here you can see all the design suite we have, and power supply design suite is something in that we have all these templates here, right? So we have a half bridge template. I can unpack it here, and you can see that you can see this half bridge LLC is there. I see some question here. I will get back to you. I can't able to read it. I will let me just finish some of these slides. This particular, I've already opened it actually. It's a full bridge. We have half bridge. Then we have this one is the new one we have added, and this one here is a fourth order. This is like a modified LLC. You can have a external inductance on secondary side, or you can include as a part of your transformer too. So these are the templates we have, and how it works is that if I run this thing, so okay, so let me show you that this is input parameter you have here, right? So this is actually, this application is defined for your 30 to 420 volts. It's your solar micro inverter DC-DC example. So this is the DC-DC stage of that solar micro inverter. In that, requirement is to have your input is changing from 20 to 40, and your output requirement is 320 watt and in power, and 420 volt in your output voltage. So what I have done here, actually, I have selected 0.3 as a quality factor, 6 as your parallel to series ratio. And so we don't have to do anything. This is basically done. So this was done at 27 volt, and you can see that we are well regulated at 420. So this is the result we got. And what's in the control part, this is not perfect closed loop control. This is a this is a feed-forward control, in a way that we are finding out how much gain we want to have a 420 here based on your changing voltage. And so we find that frequency, relative frequency, then we multiply with the resonant to get the operating frequency. Here I can, so for 27, you see that you need a 0.8 relative frequency. If I change it to 33 or something, update the file here, I will again run it. And you can see that, yeah, within few seconds, I have a 420 volt, well regulated. Now I have gone above resonant. You can see all the currents are in continuous current mode, and we have a 1.21 relative frequency that is above resonant. So you can do anything. I mean, you need to change the voltage here within the input range. So you can also go to your this limit, the worst case condition, that is the update the file and again run it. And you can see at the lowest voltage how much frequency you need here. So actually for that, of course, you need gain around 1.5. And you find out, again, it's regulated at around 420. And you can see how much DCM you have gone here. So we have gone too much below resonant. That is around 0.56. So that's your K relative frequency here, right? So this is going to multiply with your resonant, that resonant frequency, that is 200 here right now, time being. So you can do all these things, and you can also change K. Let's say you think that 6 is too high and you are getting you're going too much below. You can have a lower K so that you can have a much higher gain at the lower value of frequency. You can run it at 4. And I'm not sure how much you got 420. So you can see how well regulated this is. So I'll talk about this lookup table. This is a time domain. So you can see now at 0.65 only at the lowest, because of you have lowered the gain. Because of this, you will have some circulating current, but from 0.56 you have gone to 6.5 to regulated. So this is much better. We are much closer to resonant, but of course you have a lot of other things to take care of, your turn-off current, circulating current, and all those things. So this is something we have here. So this tool is again the time domain based tool, and if I run this thing, so this run at this particular, so by default it will be 0.75. If you want to check at your 0.665, so this is the same as this. I mean, all your parameters is like this. So this is an open loop. Now, since because of the lookup table, since you have found out that this is your frequency, you can use this to check it, right? So let me just put 6.5 or whatever that was, right? So you can basically check at 6.5 you 1.5 gain you wanted. This is all self-explanatory. We are calculating gain, and we have this much gain range to calculate from, right? So this is a very handy tool to play with. You can change anything you like you want to go above resonant, you want to go, you can do that too. You can actually at resonant, you can go and calculate. You can see that at resonant all are there. You can 1.5 you can go. So this is a very fast instantaneous tool to analyze the waveform of one cycle. So you can see if you go back and simulate, you will get the same waveform shape in the one cycle. And you can do basically anything. You can change back the K here. This is a fun calculator to calculate quickly any parameter you want for resonant. And so this is there. And here we have a design curve tool, which is actually going to help us in. So let me run it for like a large steps. It will be very quick. So what this design curve is doing is that it's same like this. We'll talk about the Excel file later. So it's same parameter you put here, you have here for same application, and you run it. So for first output panel, you have a gain curve versus frequency at different value of K. I mean, you can read these things. So this is at different K. Different K is like 4. One is 4 and one is 8. Your step size is, you can have a more finer step size to get more number of gain curves too. And this is a gain curve in time domain, like I've been saying from the beginning, that it starts right from the GVS boundary. So you have your DCM mode is there. In literature, it's called PO mode. It's a boundary of PO and PON mode. From there, we have GVS GCS boundary. We are starting all these gain curve, and this is at your gain curve at different values of Q. So I just wanted to see few curves. You can have properly. You can compare many curves, as much curve you like. And so this is, and since you run this thing with this Excel file is generated. So this Excel file by default take this application into account, whatever you put it here. And for this, in this gain, this K range and Q range, actually it's calculated your for you, actually our gain requirement is from 0.75 to 1.5. So we calculated the frequency, the extreme range of frequency, the lowest and highest frequency. For lowest frequency, we will have our maximum gain, and highest frequency, we will have the minimum gain, right? And all these things like your, I have to actually increase all this peak value, RMS value at one shot, it's calculated, and you can actually select whatever QK you think is giving you the narrowest range of frequency or narrowest range of RMS or whatever, right? I mean, it's just up to you to choose. I mean, you got the idea what I'm trying to say. And also your component values is right here. For component values, also you can come here and see in parameter file too. So these are some standard equations to calculate your LSCS LM in time domain. So values, so you can see all these values are already calculated for LSCS LM and all. So this is just one template. Similarly, we have a half bridge template here. So for this, we have again, you can come here, and if you right from the beginning, you can unpack this thing. So this is going to be like. Oh, sorry. So you can see that I have unpacked this. You can run this thing, and actually I have my settings. So this is designed for actually 24 volt, right? You see here. So this template is designed for 400 max to 24 volt for your charger application or 500 watt. So you see again, it's easily you go to 24 volt, and similarly you can see the value of from the probe, how much the frequency was needed, around 0.8 based on the gain we wanted here. Similarly, we have now this template, new template. Here I have changed the application to 6.6 kilowatt. This is quite a popular application these days, 6.6, 3.3 for your EV onboard charger, based on your stage you want, I mean, or the kind of converter you're using. So for anyway, I have designed this for 6.6. Same way, I mean, if I run this thing, let me just run it. So it will take a few seconds to run. And actually, I just need to see view, right? So I can come here and check my view. So we wanted view to be around 350. So one thing I forgot to mention, in half bridge, when you can see it's a constant voltage, right? And in the full bridge also, we wanted constant voltage. Our input voltage was changing. We can hear actually our output voltage, there is a variation in output voltage, because in OBC application, we are aware that in constant current region, there will be, your voltage will be changing, right? Typically it changes from 280 to 450, or based on your application or data sheet, you can check with them your battery, how much variation you want in output, right? So here I actually put it 350. If I put it here 452 and update this thing and run this, and let me run this thing. So it will be, so this was 350 we wanted. Here, if we change back to 452, we got 450 we wanted. So so this, and also you can see other waveforms if you like. There is no problem. LSCS LM. So you have a two capacitances on the other side. So we are seeing your current and on the both side basically, and your also with that we can have a steady state solver, and this solver is going to do the same thing as your Resonant LLC. So I click it here, and you can see it's very quickly calculated for one cycle. I think it's at the same stage. Let me check. 0.72, 0.72. How much is your? So you always need to check how much in closed loop you got this frequency. So 7.25 to match the perfectly. It's 7.25, right? So yeah, okay, fine. So 450 is voltage here, right? 450 we have. And actually, this has a problem with the sizing, right? So anyway, so this voltage, this is for Resonance CLLLC, you see. So this you wanted for your 450 output you wanted, all these your current waveform, resonant current waveform, you can see on primary and secondary side. Similarly here, it's so you can do similarly change anything, and within second you can see at new operating point. What I can do now is that go back to my slides and finish it. And if there are questions and other things, then we can take. So this is actually, there was one last template, was a fourth order, right? So this is the fourth order template, right? So fourth order means that there is an inductor on this side. So this inductor, you also can put it here. And you can see all this calculation for different inductance ratio for different, if you have a is here, right? Some standard calculation based on, you know, if you, when you select the two inductance ratio, you do it here to get your perfect value of your inductor and capacitor, and taking into account your quality factor too, and your resonant frequency, right? So this is also a good topology, alternative to LLC. Of course, when you have one extra element, you get more degree of freedom, and you get, actually LLC has a unity 1 at your resonant frequency. So these topology higher order can be used to have a better gain, more than unity gain at resonant. Sometimes when we design at resonant, our transformer turns ratio is fixed to operate there, right? So for that reason, if you want your nominal to be at resonant, but you don't want to sacrifice the gain if you mismatch some turns ratio, in that case, this topology help a lot. You can always play with the two turns ratio, two inductance ratio, air gap here to get the amount of gain you want. So anyway, so these are the things. I mean, and then I can come back to the slides to finish this presentation. So yeah, so this template I already shown to you. And so essentially, this is what I wanted to talk here. I mean, I will not read all this. You can have the slides and you can read it. So if you see this green one here, so I show you the design curve, right? So this is actually from time domain. You see, in time domain, we will have this kind of a trend from a GVS DCS boundary. But if you see with the fundamental harmonic approximation, there is no correlation, right? There is no how much error is there. There is although this error looks like a 30%, 20%, but this is a too much error when you multiply with the input voltage and turns ratio. So you can understand, if you go away from resonant, you have error with your this FHA method, which is popular for resonant design. But of course, we know that that's not accurate. So the whole rationale or the idea for the design tool for resonant is that we wanted to give you an accurate model, design curves, or steady state solver tool, so that you can you do not have to think that if there is any mismatch in frequency or error or any other thing. So yeah, so I just put this is another example, telecom, where we want to regulate from 400 to 48. We have a 10% variation in input. So I will not run this thing. Actually, the results are here. The slides. It's the same way we have designed it here. We selected one quality factor and K, and the result is at the worst case condition, extreme input voltage minimum, and then maximum, I believe. Yeah, at maximum I've shown that it's so of course at below we have wanted to go more gain, so we go on below resonant 6.8 to have this there's a DCM, you can see right away. So 1.25 gain we wanted, and then in when the voltage gone above the nominal for 80, so to get the 48 we have to get the DC gain lower than 1. So for that we have to go 1.43. So these things are there in the slides. You can have a look later. This is at resonant, as obvious, right? I mean, at 400 volt we want 48. So your turns ratio is directly your your rated by rated. So you got you at resonant condition, you got this. So this is the design flow actually working in our design suite, or the templates. That you put the specs, we calculated the turns ratio based on your output variation, or if you have a fixed output or a fixed input, or if you have a variation in input or fixed output. There's so many cases, right? So we have a template that support variation in input as well as variation in output. So based on that, you calculate the turns ratio. You can also modify it, right? If you think that you have a better way of selecting turns ratio, or you got something turns ratio in experiment, you can put it there, because once you do the experiment, maybe you do not get the turns ratio. Ideally, you calculate it, right? So you can come back and put it and always redo this thing. And we calculated the mean max because we want to calculate the frequency within this gain range, right? And within this gain range, we are optimizing your magnetic ratio and Q based on all these the peak, RMS, and the average values of your switch current, your diode current, or magnetic circulating current, and all this we take into account. And so this is a very standard way of optimizing a resonant converter, LLC converter. Go in an iterative way to do that. So you can you can have this slide. And so these are some of these design files we have done a webinar recently too, so all these examples are covered, and I have a PDF also, all the example files where you can see these being been operated, and all your design parameters calculated, and your frequency range and everything is calculated. So I can send the PDF file and the example file. And actually, you do not need the event design suite to run this thing. You can, if you are a PSIM user, you can easily run this applications. And so benefit, I will quickly go through that. I mean, some of the benefits are quite self-explanatory. It's very fast. You have seen how fastly we designed for different applications, and we are supporting different tank. So these smaller ones are easy to get. You can put some magnetic ratio, capacitance ratio to 0 or infinite to make it into from higher order tank to lower order tank. Right, so steady state solver is, like I said, we have seen is very fast and accurate to analyze it. Design curve tool for your you can have different comparison. It will help you in your iteration with the Excel file. And we have this all these cutting edge examples being supported there. And lookup table help us quickly in getting the frequency, because in DC-DC converter, we know the formula for buck converter that from 12 to 6, your duty cycle will be 0.5. But for resonant converter, LLC converter, or any resonant, it's very difficult to anybody to say that, okay, what should be your precise frequency at that particular input to get that particular, right? So for that, what we are providing this lookup table, and actually the whole design suite to give you a precisely what frequency you need. I mean, you've seen that. I mean, that how precisely we calculated all these things, right, in the different examples, right? So yes, so this is what, and all these benefits are there. And here is our link to our resources we have, and we can go and see our webinars or other application note tutorials, blogs, case studies we have also in our website. You can request a trial if you if you want to play with these tools I have shown you. We have contact person. So Albert Dunford, you may be knowing him. You can always learn something from him. He knows our SIM inside out. If you have any question, we can always contact him. This is me. You can also get back to me if I don't know answer or anything. I can check with my team, my development team, my support team to get back to you. Support also, we have a very strong team there, and we all try to help users as fast, as quickly as possible. So this is what I mean, might talk this presentation. I can take questions if you have, and the PDF I can show you is right here. These are all the design examples. So all these design examples are here. I can say it. So it's the same examples. Like I was saying, we have selected the particular Q and K and optimize it, right? So you can have this PDF if anybody interested in playing with this. And also I will send the example files with this if you are interested, anybody. And PowerSIM team can contact us, or the PowerSys team can also get back to them.
Thank you, Amit, for a nice presentation.
Yeah.
I have one question sent to me by message. Is it possible to change the PSIM schematic and still get an accurate LLC converter?
Sorry, can we?
I will copy and paste it for you in message directly so you can read it.
Okay, you will send in chat. Is it possible to change PSIM schematic, still get an accurate LLC? Yeah, I mean, I believe he means whoever is that he wants to edit LLC. I mean, if you want to include like here is this. So here I have edited this thing. So this half bridge topology was here, right? So what I did, I wanted to include some parasitics. So I wanted to because there is a turn off loss, right? So we want to reduce these turn off loss. For that, I added a MOS parallel, right, with the MOSFET, and also the level 2 you have made. So for that, of course, we get somewhat close to what the tools are predicting, but it's obvious that if you include more parasitics within reasonable margin, there will be some error within 5%, within 5%, 2% error. Even you do experiment. I mean, when I was doing research, I check with PSIM, whatever result we got, also with the hardware, it was very close enough with the experimental result we wanted. I mean, the tool too, that tool, with the tool, whatever analytically I calculated, and PSIM and the experiment, they all matched. And so there is one or two conference paper on that too. If anybody interested, you can go and check the experimental result too there, and also the results we have gone from here. So yeah, you are easy to edit and include anything you want in with this LLC converter. Actually, here LM is included here. We see there is so much parasitics included here within your actually 3-winding transformer, right? So and also we have different application notes we have written. I mean, it's coming. We have included thermal devices. We have actually for battery load we have considered too. I mean, we have basically edited this template to include the battery load because we wanted to design that 3.3 kilowatt or 6.6 kilowatt with the battery, proper battery load with constant voltage mode and also constant current mode and all those things.
Thank you, Amit, for your answer. I have another question. By message, could we implement a different control stage as well? I sent it to you.
Can we implement a different control stage? Yeah, definitely you can. If you let me see, I open one example in desktop, right? Let me. Why is it right? Okay, so here's we have a closed loop outer board. Okay, here. So you see here, actually what we did, we optimized this Resonant LLC. I mean, in the design template or design suite is to optimize the tank values and the operating range, frequency range, and all those things. Here I am strictly using dual loop PI. You see there is an inner current loop working here. I can run it too. And there is an outer voltage loop too. And this is actually in digital domain. I mean, we first we did AC sweep and use smart control to tune these PI parameters and everything. So that is all is something you can always edit, and you can do your own control if you like. If you have any nonlinear sophisticated control and all those things, you can do it too. End of the day, you want to regulate your voltage, current, or whatever application you have there. So you can see here that you have so what we did here, we changed the load here, right, from 50% to 100%, and you can see still we wanted 420. So this is again 3.3 kilowatt 421, and we are in your when we change the load, also we got back to 420 we wanted. So controller is working fine here. And here there is no need of that lookup table. It's the controller is good enough to calculate the value of your operating frequency, right? So you can see 0.8 or whatever needed for this application.
Thank you, Amit. I have a question. I'm sending it to you right now.
Do you mean OB? You mean onboard charger? Yeah, yeah. It's actually, I can show you the onboard charger application implemented. If you want, you can we can send that. This is still in the pipeline. Our these app nodes. We are having a new release within weeks. All these application node will be available to you. Let me just open this example. These are recent examples, and you see here. Okay, there is a proper battery load for your OBC example. So you have a, I will not run this. This takes too much time to run. We have a first constant current region and then constant voltage region. Actually, I may have a SMB file. Let me just yeah, here is SMB file. So you can see here that you have a your I battery, V battery. With a proper battery, your this thing is working. So you see, first you have a constant current mode, and then you have a your state of charge is going right. Our initial state of charge was around 60% in this example, and finally we wanted 420, right? So if you first we wanted the constant current around 7.7 amp for 3.3 kilowatt at output current, right? And then we wanted 420. So that's also we have achieved here. Yeah, and your current has gone to 0, and we have gone this 420 we wanted. Yeah, so you can actually see this y-axis is very zoomed here, right? So actually it's very 420, right? With this ripple you see is negligible, right? This current is close to 0 and voltage is 420, right? Reduce the ripple. Yeah, another question I see. Yeah, you can have you can play with this filter transformer, right? For this filter values, right? It's 80 right now. We can have a better. We have a CLLC filter to some pipe filter or other filtering you want, or you can actually increase some cap value. But what happened? This cap value is it change your control dynamics, right? You have designed the controller this PI gains based on this one particular set capacitance value. But after the result, you see that it's still some ripple. So you have to adjust those ripple somehow with your so that you do not affect your control dynamics too much, right? So yeah, these are very fundamentals of any power converter, right? So you can see here 2 micro was used for low voltage to high voltage. So here our output was 420. So this is a low current application. So turns ratio is from low to high. And in half bridge, actually we have a 100 micro to reduce the ripple. We cannot have a same cap for this same application. So this has a different application. This is high voltage to low voltage. So here our cap is 100 micro, right? So you have seen its turns ratio is from high voltage to low voltage. So we have in same way we have adjust this this your cap value, output cap value.
Thank you, Amit.
Yeah.
I don't see any other question. I want to say a big thank you to you, and thank you also to all the attendees that participated in this last session. I hope you enjoy your time with us during this week.
Yeah, so there is no other question, Matt? There is no other question?
Okay. No, I don't see any other question. So if people have questions later, you feel free to contact Amit directly via his email address or directly into UVA, or you can contact us at PowerSys, and we can also provide you technical assistance or give you the address if needed.
Yeah. If you need, go ahead, Matt. Yeah.
No, if you have something to sell us, you can go ahead.
Yeah. I was saying that you can, if you need any design files, slides, design examples, you can contact me or the PowerSys team. We can send back to you. If you want to have a recording of this presentation, PowerSys team can get back to you too. And you can also directly ask us or get back to me too, or anybody in PSIM too. And yeah, thank you so much, everybody. And I think this is the last presentation or last day. So yeah, I wish all of you all the best. And Adrian and Matt, bonjour.
Thank you, Amit. So now we will have a final session from our marketing manager, Frédéric Perret. She will say final words and closing remarks. So you can directly go back to your agenda and tune in for the final and last session from Frédéric Perret. Thank you, Amit, again. Thank you, everyone. Have a nice day. A great weekend ahead. Bye-bye.
Merci, everyone, and have a nice weekend.
Thank you. Bye.